Okay, so we'll go back to another video. Here's a nice little trigonometric integral we're dealing with from 0 to pi, and then inside of our function we're dealing with, of course, trigonometric functions, but also the absolute value sign. So we have x times the absolute value of sine of 2x divided by 3 plus sine squared of x, then dx. So a lot of this stuff is, well, the first thing is that we're going to be using a nice little property. This is our first step that's actually going to be, it's going to change things up from how we rewrite our integral. And then after utilizing that property, there's going to be some things that we're going to be using in terms of the properties of the absolute value sign symbol, which that's going to be quite the game changer there. And then following that is, you will be using a bunch of other calculus techniques. Specifically, we'll be using some u-substitutions and then to make the evaluation easier. So we got two different things that we're going to actually be not proving, but like the properties we will be utilizing to help, make the simplification a lot easier, and then calculus techniques along the way. So that'll make things a lot more nice and interesting. So with that, why don't we actually just jump right in? So let me call this capital I. This will be important later on while we do this. So you guys remember King's rule back in the day in early calculus? So this is actually our nice little rule that we will be utilizing to rewrite our integral. So this says for a definite, the definite integral from our bounds from a to b of f of x dx. You can actually write this in terms of like the difference of the distance, but it's still the same thing in terms of the integration, to say that a to b for our bounds, and then this time our function is going to be, you add those bounds, a plus b, and then subtract the distance from x, and then dx. So we will be utilizing this to actually rewrite our integral. So with that being the case, so now rewriting our new integral is going to be from 0 to pi, then substitute x in terms of a plus b minus pi. So in this case, this is going to be pi subtract x. And then now the absolute value of 2 and then times pi minus x. Close that off, and then on the bottom, so that means 3 plus sine square of pi subtract x, and then dx. What's also nice is that there's some things that can actually be simplified down easier. So simplified down, so 0 to pi, so then I have, of course, pi minus x, and then inside our absolute value, sine of 2 times pi minus x is there. That's going to be the same thing written as negative sine of 2 times x. And then on the bottom, so that means sine square of pi minus x, that's of course still going to retain the same identity of just sine square of x and then dx. Okay, so with that being the case, and then what we can do here is that, of course, this can also be rewritten such that the negative, because of inside our absolute value function, it'll still just remain as positive. So basically, to simplify it down just even further down to the simplest as it can, this is just from 0 to pi of pi minus x, and then simply just the absolute value of sine of 2x, and then all this being divided by 3 plus sine square of x, and then dx, which is still, of course, equal to I. So two of the same identities. So what I'm going to do here is, of course, we're actually going to add both those identities together. So we have a 2 times I. So we're actually adding this function, and we're going to add this integral, and then we're going to add our given integral. And so what doing so is actually going to nicely reduce down to simply just, so 2I. So of course, there's a pi minus x, and if I add the x over here, those x is just going to cancel. So we're just left with 0 to pi of just pi, and then multiply by the absolute value of sine of 2x. Then we close that off, and then 3 plus sine square of x, and then dx. And then what we can do here is our sine of 2x of the absolute value. We can actually divide this up for our bounds, but also change that so we're dealing with the positive and negatives. So, and then the pi can be factored out outside. So it's pi, and then here's going to be 0 to pi. So that means we're dealing with the positives. So actually we're bringing up our bounds specifically from 0 to pi over 2, and then pi over 2 to pi. So the first one, 0 to pi over 2, and then we're just left with the positive of sine of 2x, and then 3 plus sine square of x, and then dx. And then we're going to be dealing with the negative from pi divided by 2, and then to pi. So of course, factor out that negative, so that'll be a minus over here, so minus pi, and then 0 to pi of sine of 2x. Well, I also got to change this bound here. So that should be pi divided by 2 on the lower bound there. And then 3 plus sine square of x, and then dx. Okay, so here's a little note that I want to make before we actually continue forward. We know the nice little identity that sine of 2x. We know that it has the nice identity of just 2 times cosine of x and then sine of x. This will be important later to use the identities to reduce things nice and simple. By doing so, that means now, first I'll just replace the identity back into over here. So that means we have pi and then 0 to pi over 2 of just sine of x, or well, this should be really 2 times sine of x and then cosine of x. So 2 sine of x, cosine of x, divided by 3 plus sine square of x, and then dx, and then subtract pi divided by pi, from pi over 2 to pi, and then this is going to be same function again, so or integrand. So 2 times sine of x and then cosine of x divided by 3 plus sine square of x, and then dx. Now, this is great, so we can actually utilize a u-substitution. So we're going to let u equals sine of x, so that du is then just equal to cosine of x and then dx. So of course, this being the case, we have to change our bounds. Don't forget to do that. So that means if I plug in pi over 2, that's just going to be 1 on the top. If I plug in 0, that's going to be 0 on the bottom. And so this will just be 2 times u, and then cosine dx, just replace that with the du. And then on the bottom, this is going to be, I'm just going to write the u square out the front first. So u squared plus 3, then du, and then subtract, so pi, and then, so change our bounds yet again. So let's see, pi, so that's going to be 0 on the top, pi over 2, that's going to be 1 on the bottom. And of course, so the same thing, 2u, and then divided by u squared plus 3, and then du. Okay, so that means 0 and 1, we'll have to flip that, change our bounds of integration, so that'll become a minus, but then that turns out to a positive. So we can actually add those together because it's actually in the same bounds, but also in the same, the same integrand as well. So that becomes a 2 pi, and then our bounds from 0 to 1, and then of our function, our integrand 2u, and then u squared plus 3, and du. Then guess what? Just utilize another u sub. We're going to call this v. So let v equals u squared plus 3, and then dv is then just equal to 2u du. And that's great. Then can they just simplify some things out? So then 2 pi, and then I'll change our new bound. So 1, this is going to be 4, plug in 0, this is going to be 3. So then this is just 1 over v, and then dv. So then, of course, that's the easiest integrand or antiderivative to find, which is just the natural log. So 2 pi times the natural log of v, evaluate this from 4 to 3. And so evaluate further, so then that's the same thing, and also utilize the natural log property. So I have 2 pi of the natural log of 4 divided by 3. But that's not the end of it, because that's just equal to 2i. So just divide by 2. So therefore I, our given integral that we're trying to evaluate, is then just equal to the natural log, or pi times the natural log of 4 divided by 3. And indeed, with that, that is our final answer to our trigonometric integral utilizing the absolute sine value, and then the trigonometric integral sine squared and then sine. So everything together, just using one nice little property, using the properties of the absolute value function, utilizing both its positive and negatives behavior. Then everything here just comes down to just simple calculus techniques from u-subs. So yeah, that's pretty cool if you ask me.